The increasing demand for energy, currently based on fossil fuels, is taking us to the point of no return in global warming and climate change. The use of hydrogen in fuel cells is one of the prime contenders when it comes to providing an ecological and renewable solution. Water is a universal source, which provides abundant and accessible hydrogen. Through breakdown processes or photolysis, it is possible to extract hydrogen from water, as do plants through photosynthesis, our planet's main energy force. In this way, low-energy bonds are reorganized into more energetic hydrogen and oxygen bonds that allow us to store the huge amount of solar radiation that we receive in a kind of natural battery. The sustainably produced hydrogen would be used in efficient fuel cells to generate energy, once more resulting in the production of water and reducing CO2 emissions. We are at a crossroads and face a paradigm shift towards a global personalized energy model through artificial photosynthesis, with the sun and water as the main driving forces. In our MAGEC project, photonic and electrochemical nanotechnology are combined with the objective of improving the sustainable production of hydrogen. In particular, our research focuses on the conversion of infrared energy from incident solar radiation into visible ultraviolet energy through photonic processes and luminescent material doped with rare earth elements, with the objective of increasing the efficiency of these water photolysis processes. MAGEC is also in the process of developing the study of semi-industrial and sustainable exploitation of the extraction of hydrogen from seawater by using traditional salt pans as a system of solar photoreactors, thereby taking advantage of the disused infrastructure present in the Canary Islands. As an added value, MAGEC also plans to take hold of the great potential of the mineral resources from rare earth present in rocks and sediments in the Canary Islands, as well as the abyssal sediments on the ocean floor, which might have significant concentrations of elements that can be considered strategic for contemporary society and the technology industry. Thanks to these processes of conversion of infrared radiation into visible ultraviolet in our luminescent materials, our research team has already achieved significant improvements in photocatalytic processes. In particular, we have demonstrated an improvement of 20% in the activity of one of the most efficient commercial photocatalyzers in the degradation of organic pollutants in water with solar-type radiation. These results support the viability of the manipulation and transformation of incident solar radiation to improve the production of hydrogen in photoelectrochemical cells. Thus, the objectives of our research project are, firstly, the design and synthesis of new luminescent materials doped with rare earth with the ability to convert infrared solar energy into visible ultraviolet energy, and then their application in the increase of the efficiency of significant photocatalytic processes such as the breakdown of water into hydrogen and oxygen and the degradation of pollutants for water purification. The research developed in the MAGEC project proposes interesting technological applications in priority areas for the sustainable generation of hydrogen from water through solar energy in order to reduce CO2 emissions, and ultimately arrive at a situation where no fossil fuels are used and all energy sources are renewable. In this regard, the Canary Islands can position themselves very favorably when it comes to the development of these energies by proposing a sustainable energy model. Together with the possible semi-industrial application, the use of the traditional salt pans of the Canary Islands, and the promising geochemical analysis of rare earth elements in rocks and sediments on the ocean floor, lead us to anticipate a significant technology transfer of the results in the short term and medium term in the form of patents or utility models. We are also ensuring the dissemination and publication of the project results via the team's main website as well as through other channels of communication such as press releases, exhibitions, seminars, and talks. Our main line of research focuses on the synthesis and characterization of materials doped with rare earth elements. Glass, crystals, nano-vitroceramics, nanoparticles, light-sensitive resins, all of them for the transformation of infrared radiation into visible ultraviolet. To this end, we analyze their properties in our optical spectroscopy laboratories, and then continue our experimental testing of photocatalytic activity in the chemistry laboratories. At the same time, we are also exploring the potential of the sedimentary and magmatic rocks from the ocean floor of the Canary Islands. We already have a collection of samples from various seamounts which provide promising mineral source of rare earth. Finally, we have also considered the semi-industrial exploitation of the salt pans as a photoreactor system for solar generation of hydrogen from seawater and have published the results of trials and pilot laboratory studies. Looking ahead, we expect to complete a viability study and possible semi-industrial exploitation of salt pans as solar photoreactors for solar generation of hydrogen and seawater. In this regard, it is important to note that researchers from the University of Stanford and Harvard in their recent publications have mapped out a global scenario in which the avant-garde technology of artificial photosynthesis plays a vital role in energy sustainability. By using the metropolitan coastal installations to capture and store solar energy, consisting of shallow water floors with photoactive particles to catalyze seawater. Lastly, it is important to emphasize that our project proposes a multi- and interdisciplinary research study of material science, addressing significant challenges with regard to actual problems related with energy and the environment. But we also suggest they should be applied in other areas associated with medicine, especially in the development of tumor phototherapy and biomarkers, and the synthesis of biomaterials using modern 3D techniques.